Our next speaker is Vedika Khemani from Stanford, who is talking about topological quantum spin-glass order.
I don't think, oh, okay, good. Thank you all for being here, and thanks to the organizers for the opportunity to speak at this conference. My talk today will be on a striking new phase of matter, a topological quantum spin glass. As the name suggests, this phase marries the physics of topological order with the physics of spin glasses, two phenomena which both lie outside the Landau paradigm for phase classification and which have separately defined many breakthroughs in many-body physics over the last 50 years or so. This phase also has consequences for information theory, and it describes a qualitatively new mechanism for obtaining a quantum memory, and it describes the physics of certain families of recently discovered error-correcting codes, the so-called good quantum LDPC codes. So, stepping back, an overarching theme of my talk will be the close relationship between the field of many-body physics and the study of information and computation. As we all know, ordered phases of matter play a big role in computation by furnishing natural physical mechanisms for robustly encoding information. A familiar classical example is the magnetic hard drive, which in a ferromagnetically ordered phase, we know that there are two degenerate symmetry-broken ground states, which have macroscopically different magnetizations. These are related by the action of the Ising spin-flip operator, for instance. If you think about an Ising magnet with the all-up and all-down states, and these can be used to robustly store classical bits, even in the presence of noise, which can flip individual spins, but won't change the global magnetization. In contrast, a quantum bit or qubit must be protected not just against bit flip errors, but also against phase errors, and this requires a qualitatively different mechanism. And Kitaev's breakthrough realization was that different states of a logical qubit can be encoded into highly entangled topological states, which are locally indistinguishable, but which hence furnish robustness to noise. Just for specificity, Kitaev's toric code is defined on this 2D lattice. They're physical qubits on edges, two encoded logical qubits. All the logical states satisfy these local commuting X and Z type stabilizers. And these logical states are highly entangled. I guess you can't see my mouse. They're highly entangled when written in the physical basis, differing only by these global X and Z operators, which wind around the torus in some topologically non-trivial way. Again, making the connection to many-body physics, the checks of the toric code also define a zero correlation length fixed point Hamiltonian for the topologically ordered phase of the well-studied Z2 lattice gauge theory. These code states label the degenerate ground states, and the entire phase has robust ground state degeneracy and anyonic excitations corresponding to the X and Z violations with non-trivial statistics. So the features of local indistinguishability, which make the topological phase stable, also endow the code with robustness to noise. So to summarize, the two paradigmatic phases or classes of ordered phases of matter, which is symmetry breaking and topological order. Actually, topological order now is also understood as a new kind of symmetry breaking, that of higher form symmetries, but I don't need to get into that. These two paradigmatic classes of symmetry breaking, of ordered phases, also are used to robustly encode information, whether classical or quantum. And the physical principle is that the symmetry breaking furnishes a degenerate ground state manifold with the different states differing by the action of the symmetry operator. The symmetry operator is generally going to act on a macroscopic number d. D is the code distance of qubits. So in the Ising example, it's going to flip all the spins. In the toric code example, it's going to act on this loop operator which winds around the system. And if you have a ground state degeneracy of 2 to the k, then we can encode k logical qubits into our system of n physical bits. And of course, the magic of the threshold theorem is that by increasing the number of crappy physical qubits that we have, by entangling more and more crummy physical qubits, we can get a logical qubit which gets better and better if the code distance diverges with n. And after many years of this being formulated theoretically, this was recently demonstrated by the Google group late last year. Okay, so all of this understanding of phases of matter and the codes built on them was inspired in condensed matter physics by the study of materials in nature. However, some of the remarkable new experiments which are implementing these codes look nothing like rocks in nature, right? So this is a video from Misha Lukin's group, which you'll hear about tomorrow. The theme of this conference is quantum simulation, and a major goal of quantum simulation is to use these experiments, these new experiments, to simulate these rocks. And that's a great goal. However, these novel experiments in these synthetic devices, these large classes of synthetic devices, also present brand new opportunities and brand new frontiers for many-body physics and quantum simulation. Okay, these experiments have extraordinary control over individual quantum entities and their dynamics, and they allow us to study emergent phenomena in new regimes beyond that which simply exists in equilibrium in nature, and indeed, even in new types of geometries, such as these non-Euclidean graphs that I've drawn in the corner of that paper. Okay, so the work that I want to tell you about today brings together these two new regimes of many-body physics, non-equilibrium and non-Euclidean, to define a fundamentally new phase, which we call a topological quantum spin glass. Okay? And this is indeed very much motivated by new frontiers in quantum simulation. And one message that I want to bring across is that we should think of quantum simulation more broadly and not just think of it as something to simulate kind of physics that exists in rocks in nature, but to define new physics that we can probe with these new experiments. Okay. So before delving in, I want to take a moment to highlight our main results. So as I was saying, we find a new phase of matter, a topological quantum spin glass. This phase has a provably rugged free energy landscape. So when you think about spin glasses, you have in mind something that's sluggish, that's glassy. A picture that people often have in mind is that you have a free energy landscape with many local and global minima, and separated by macroscopic barriers, so that if you start in one of these minima, you can get trapped there. Okay, so this picture has only been kind of rigorously verified for certain classes of very highly connected all-to-all models. But in the models that I'll tell you about today, you do have a picture of such a complex free energy landscape. However, unlike classical glasses, the nature of the memory is going to be completely different. Okay? Each of these wells in this landscape actually hosts a highly entangled topological state at finite temperature. And this nature of memory, which I'll describe, gives you a way to robustly encode passive quantum memory using a different mechanism, the different mechanism being this kind of topological quantum spin glass. Okay? So prior to this, there was kind of one picture that we had for how you can robustly encode quantum memory, which is through thermally stable topological order. And as Al mentioned, that requires us to be in 4 dimensions or more in the standard kind of picture, for instance, in the 4D toric code. Okay? But glassiness gives you a new way to encode memory passively, so that's the self-correcting memories. And the topological nature of the glass allows the nature of that memory to be quantum. Okay? En route, in thinking about this question, we actually ended up making progress on a very long-standing question in the study of classical glasses. And what we were able to do is give a rigorous and transparent derivation of spin glass order, which I'll define for you, in a model with finite connectivity. Okay, so far there had been many pictures, many heuristic methods, but as far as we are aware, the only rigorous proof of spin glass order through replica symmetry breaking was in an all-to-all connected model, such as the Sherrington-Kirkpatrick model, for those of you who know what that is. But in our models, the graphs that we will study have finite connectivity, so every node only talks to finitely many other nodes. And we're still able to give a rigorous proof of spin glass order at finite temperature in these models. And the most attractive part of this proof to me is that this derivation is completely transparent. It relies on simple Z2 linear algebra from the theory of codes, and there's no replica symmetry breaking. It implies replica symmetry breaking, but it's actually very, very physical, and you can directly see where the glassiness comes from. Okay? En route to proving these results, we also proved another technical result, which I think is of independent interest. This is generalizing a very well-known theorem called the Markov chain bottleneck theorem, which has been studied in the context of classical Markov chains, to quantum dynamics. Okay? And this gives us a perspective on how to think about quantum phases and phase transitions in open quantum systems and at finite temperatures in a much more kind of rigorous way. Much of our understanding of phases and their stability has to do with ground states and in particular gapped ground states, but this allows us to take steps forward in these other settings. And on the information theoretic side, this theorem also helps us bound the performance of certain quantum Gibbs samplers, which are algorithms that have only been developed in the last 2 or 3 years. Okay. So that's the upshot of what I'm going to tell you. So if I don't get through all of my talk, those are the messages. And before moving on, I want to thank my collaborators, and particularly to call out Benedikt Blake, who's an amazing postdoc at Oxford, and Tibor Rakowski, who was a postdoc with me at Stanford and has now moved to Budapest to start his group. Okay, so this work was motivated by thinking about the physics of certain new families of error-correcting codes. This was a very recent breakthrough as of 3 years ago in the study of error correction, which was the discovery of what are called good quantum LDPC codes. LDPC just stands for low density parity check. This means that every check or interaction term involves a finite number of bits or qubits, and also that every bit or qubit is only part of finitely many checks. Okay, so if you embed your code on some finite connectivity graph, there's always a graph such that this code looks local on that graph. Okay, so in a good code, K and D are both proportional to N. Okay, so this is minimal overhead. You're encoding a number of logical qubits which scales with the number of physical qubits, and it's as robust as it can be in a scaling way because D is also proportional to N. Okay. Now, a theorem by Bravi, Poland, and Turhal in 2010 showed that you cannot get this kind of optimal scaling if you're talking about Euclidean geometries and local interactions on Euclidean geometries. Okay, so you need non-Euclidean expander graphs in order to get these types of codes if you want this LDPC structure in them. The discovery of classical LDPC codes has been around for many, many decades, but quantum LDPC codes were only discovered in the last 2 or 3 years. And just to bring it home, I want to contrast the scaling with the scaling of the 2D toric code, which we talked about earlier, which has K being 2. If you're talking about the surface code, K is 1. The key point is that even if you make N as big as you want, K is just finite. Okay, so you have this large overhead, and D goes like square root of N. Okay, so this is a parametrically better scaling. Okay, so to give you a picture of the types of models that we have in mind, so we'll be thinking about codes defined on non-Euclidean expander graphs. So that's a picture for what a graph could look like. An expander graph has a defining property that boundary and bulk scale proportionally to each other. Okay, in Euclidean space, if I cut out some ball of sites here, okay, and then I ask how many sites are in the neighborhood of this ball, well, that only scales like the boundary of that ball, which is parametrically less than the volume of that ball. Okay, so perimeters and volumes scale differently in Euclidean geometries. On an expander graph, I can cut out any ball of sites, and the neighborhood set will scale proportionally to the size of that set. So a picture you can have in mind is something that looks locally like a tree. Trees have this property that the number of leaves is the same as the number, it scales proportionally to the number in the bulk. But then, because I want this to be true for all sites, you picture a tree, but then the boundaries of the tree are closed in some way, so that every site is statistically the same as every other. There's no like privileged root in reality, okay? So we look at models on those graphs. And then you just think of generalized Ising models or generalized repetition codes, classical codes. If you want a classical LDPC code, a picture for that, which is a Tanner code, is that you can put bits on the edges of that graph. And now on every vertex, you act with some small number of a small code or interactions that only act on the bits that are incident on that vertex. Okay, so this could be ZZZZ type interactions in the picture that I've drawn, but in general, that's the exact form is not so important. It's LDPC, it's local on that graph, and it's classical. I drew for you a tree-like geometry there, but actually you can also, the models, the graphs don't have to be locally tree-like. A very interesting class of expander graphs that are very well studied are these models defined on these hyperbolic tessellations, which have lots and lots of small loops. Okay, to build quantum codes, we can start with these classical codes, and we can take different products. There are some standard product constructions in the literature. You might be quite familiar with the hypergraph product. To get these good codes, you actually have to do a little twist on the hypergraph product to do what's called a balance product. But you can take products of these expander graphs, and then you get a graph where morally the expander graph is something, you get a higher dimensional expander graph, which you can think of as having these kind of plaquette-like objects. Okay, so a picture you can have in mind for what's going on here is taking a product of two circles gives you a torus, okay, and taking a hypergraph product of two Ising models on these two circles gives you a toric code on a torus. Okay, so here, I don't know how to draw it, but we're taking this expander graph, we're taking its product with another expander graph, you get some crazy looking graph, but locally you might imagine some like picture like that with lots of books and so on. And then once you have that graph, we again define some kind of generalized toric code on that graph. So you again have commuting ZZZ type terms and commuting XXX type terms. Okay? So the actual constructions in the math papers that I had referenced earlier, those are quite complex. The graphs that they can prove things for have degrees of hundreds, okay? But these simple pictures should give you a flavor for what those graphs look like, and we actually did numerics on degree 7 graphs on exactly that code there, and everything seems to numerically work, even though the proofs require larger degrees. Okay, so a question that I've been asking in my group for the last 2 years or so is, what is the physics of these LDPC codes? Okay, so as I was saying, these codes were written down by mathematicians and computer scientists. The papers are beautiful, but they take the form of theorems and proofs without much physical insight. But other models of error correction, like the repetition code or the toric code, also correspond to phases of matter that we have a lot of insight into, a lot of understanding into, and for which we have physical intuition for why the model acts the way it does as a code. Okay? So the question we've been asking is, can we think about these models as phases of matter? Are they stable to perturbations? Do they define what kinds of gauge theories do they define? Do they have topological features? So that's what we've been asking, and we were actually able to show that it does make sense to think about these models as phases of matter with some stability, which is in and of itself quite unusual because these models have finite rate. Remember, k was proportional to n. That means that the ground state degeneracy is exponentially large in n, okay? And we were able to prove that if you perturb this model, this ground state degeneracy remains robust and protected by a gap. So this is like a violation of the third law, because we have an extensive ground state entropy, which remains robust even upon perturbations, okay? But again, all of our usual intuition from StatMech is based on Euclidean geometry in which bulk and boundary scale differently, whereas this is a very different setting. Okay, so now I'm not really going to talk about the ground state physics of these models. I'm going to switch to talking about the thermodynamics and dynamics of LDPC codes and how they function like glasses. Okay, so to talk about the dynamics of memory, I want to start by just reviewing that, when we talk about a memory, we want to prepare our system in some code space, And then we want to keep the system there in the presence of noise, which is trying to take you out of the code space. So memory is then fundamentally a non-ergodic dynamical process. And what type of memory you have cares about the nature of excitations in your problem, which are trying to take you out of the code space. So a standard paradigm for memory is an active error correction, in which you should think of it as information protection via information processing. So if you, in your experiment, implement the surface code or the toric code, you're going to have noise. The noise is going to create a bunch of point-like excitations, which are violations of your X and Z stabilizers. These excitations in the 2D toric code are deconfined, so they can wander around freely without any energy penalty. You make measurements of where the excitations are, you pair it up in your classical computer, and then you keep repeating this cycle. Okay, so you can do this, but it's actually quite challenging because you have to constantly make these measurements and do this kind of non-local feedback and processing. Instead, what I want to focus on for the rest of this talk is our passive memories. And in this paradigm, one can obtain a diverging memory time simply by coupling the system to a bath maintained at a low enough temperature without the need for any further active measurements of feedback. Okay? And traditionally, this way of obtaining a passive memory requires thermally stable order. So what we have is like, how do we build a quantum hard drive? Okay? So to think about memory from thermally stable order, let's take a step back to a very familiar example, which is the 2D Ising model. Okay, so a magnetic hard drive that's in 3D, but the physics of 2D or 3D Ising models is not going to be so different from the perspective that I want to mention. So in a 2D Ising model, there is a finite temperature phase transition. That phase transition below TC, there is an ordered phase. In the ordered phase, there are two stable equilibrium states, which I've labeled here as rho up and rho down, with positive and negative magnetization, separated by a macroscopic free energy barrier. So if we start in the state with large positive magnetization, then under local Glauber dynamics, this is the dynamics that's preparing the thermal state or base detail balance, we'll quickly relax to rho up, but then stay there for a time which diverges with system size. Okay? So more formally, the Gibbs state ceases to be unique below TC. There are these two different Gibbs states separated by this macroscopic barrier. There's many ways to mathematically formalize the notion of non-uniqueness of Gibbs states. You may have heard of DLR prescriptions. There's this math textbook, which the whole textbook is devoted to that. But the approach that's most useful to us is to take a dynamical perspective which relies on the classical bottleneck theorem. And the key point is that if you look at the global Gibbs state, just e to the minus beta h, below TC, then what we'll find is that it has large weight on two macroscopically distinct parts of configuration space, with large positive magnetization and with large negative magnetization, separated by a bottleneck region, which has low relative weight in the Gibbs state. So since local dynamics starting in one component, for instance, the all-up component, has to go through this no man's land of very, very low magnetization, very low weight in the Gibbs state in order to get to the other component, it just gets stuck in that up component and stays there for a time, which diverges with system size. Okay? The time scale, the time scale can be quantified by looking at this so-called bottleneck ratio. This bottleneck ratio is just a ratio of the Gibbs weights in this kind of no man's land bottleneck region with low magnetization relative to the region with with high magnetization. And this directly quantifies and defines a free energy barrier, and it defines for you the lifetime of a component which is surrounded by the bottleneck. Okay? So this bottleneck picture gives you a way to explicitly define multiple Gibbs states, and these multiple Gibbs states give you different classical memories in this case. So to summarize, if I'm thinking about classical models with spontaneous symmetry breaking, if I'm talking about the 1D Ising model or repetition code, this has deconfined point-like domain wall excitations. There's no finite temperature ordered phase. So if I want to use this as a classical memory, I need to do active error correction. This is in contrast to the 2D Ising model or repetition code, which has extended or confined domain walls and stable spontaneous symmetry breaking order below TC. So this I can just hook up to a cold bath and use as a passive memory. The quantum analog of these problems is that in 2D, in the toric code, I have deconfined point-like excitations, no topological order at finite temperature, so I need to do active error correction. Whereas in the 4-dimensional toric code, actually both my X and Z type excitations, the flux loops form these extended loops, just like the domain walls of the Ising model. And now I can do passive error correction because I have stable topological order below TC. Okay? So these problems are actually closely related. You can again use these product constructions that I had told you about earlier to go from this classical column to the quantum column. Okay? So now, and I should mention that there's an active research area. This is the topic of fractons and self-correcting memories in 3D, trying to find passive memories in 3D, but there are no known examples as of yet. Okay, so this brings us to a puzzle because many known classical and quantum expander codes do have robust passive memory. However, it is also known that the partition function of these models looks analytic at all temperatures, so that there's no conventional thermodynamic phase transition into a low temperature ordered phase. If I just look at the partition function, it looks like that of a trivial paramagnet. So if you take this LDPC code, take the Hamiltonian defined by its Strex, and try to ask, is there a TC that you can compute? It'll just look very, very smooth, okay? So the key point is all checks are independent. They can be independently violated. So in terms of these independent checks, the model looks like a decoupled paramagnet whose partition function is analytic at all temperatures. So there's this tension between the existence of memory, passive memory, with local decoders, and a completely analytic partition function, which naively does not show any transition. Okay, and this puzzle was recently highlighted in Andy Lucas's group last year. So this brings us to another mechanism for passive memory, which is familiar from the study of classical models, which is spin-glass order. Okay, so spin glasses, as I was saying, are best associated with disordered or frustrated spin models, such as this well-studied Sherrington-Kirkpatrick model, which is an all-to-all Ising model with random interactions. The free energy landscape looks rugged, with many local and global minima separated by these macroscopic barriers. Below a dynamical glass transition, TG, each of these minima defines an equilibrium state with diverging lifetime under passive dynamics. So if you start in one of these minima and do Glauber dynamics, you'll remain trapped in there and can recover memory of that state after arbitrarily late times, okay? And the point is that this glass transition TG is a dynamical transition, which may be completely invisible in the naive thermodynamics of the problem, okay? If you look at the partition function, it's going to average over all wells at a given energy, okay? But the point is that these wells may belong to distinct ergodic components, and they're disconnected from each other, so you really shouldn't be averaging over them. And if you average over them, you can miss this dynamical feature, okay? This type of ordering, glass ordering, is also entirely distinct from spontaneous symmetry breaking because you have all of these different equilibrium states, but they're not related to each other by the action of symmetries, unlike the two equilibrium states of the Ising model, which were all up and all down and related to each other by the symmetry, okay? So in the bottleneck picture introduced earlier, each of these wells can be associated with this kind of region in configuration space separated by some bottleneck. So it defines a Gibbs state component with diverging lifetime. Using this kind of decomposition, okay, so you can concretely define what it means to have these Gibbs state components using this bottleneck picture. And then using this kind of decomposition, you can do, using these components, you can do a decomposition of your global Gibbs state, and you can explicitly define spin-glass order in terms of this decomposition, okay? So we take the global Gibbs state, we write it in terms of all of those components, and then we can just compute some standard entropies of this decomposition. So what we're trying to ask is, you know, there's a feature called shattering, which is your decomposition such that no single component carries more than an exponentially small fraction of the total weight? Okay, that's the first thing we would want, okay? That you have exponentially many components, they all have diverging lifetime, and no one component carries most of the weight. Okay, so that's called shattering. And the other feature that we would want, which we call incongruence, is that most of these components are not associated with any ground states in the problem. Okay, so even within a single symmetry sector, there are many, many, many more local minima compared to global minima. Okay, so that's the picture, but that can be formalized in terms of the entropies of this decomposition. Okay, so when we say that we prove spin-glass order, we're going to prove features about this decomposition. So the point is that using these components with memory, the system can serve as a robust memory encoding many classical bits. If you have 2 to the k stable minima, you get k encoded logical bits. So a question is, can we encode quantum memory in a similar way? Okay? So to complete the table from earlier, there's 2 mechanisms to get passive classical memory. There's thermally stable spontaneous symmetry breaking, and there's spin-glass order. For quantum memories, so far, all of the work has focused on thermally stable topological order, but we add this extra box here, which is topological quantum spin-glass order. The features of this topological quantum spin-glass phase, which we can prove exist, rigorously prove exist, at low temperatures in a family of quantum error correcting codes, the features are defined by shattering and incongruence, which is what I said defines classical spin glasses, the classical complexity of the free energy landscape. But in addition to shattering and incongruence, these models are also topological. So the picture actually looks like, you have all of these different logical sectors, 2 to the k logical sectors. Each logical sector has this crazy rugged landscape. And then there are copies of that landscape, 2 to the k copies of it. And then wells in each copy together, like the dark blue ones and the light blue ones, each family of wells can form a quantum memory. Okay, so if you look at the nature of the Gibbs state in the wells, you can first show that the Gibbs states are long-range entangled using this definition from Matt Hastings from about 15 years ago. But then you can also show that there are many, many embedded quantum memories at finite temperature. Okay, so we combine this classical complexity and quantum complexity. So that is the picture of what a quantum topological spin glass is and what features it has. Okay. So again, as I was saying, we can rigorously prove the existence of this using very simple coding theory results. And this actually led us to derive some new results even on classical spin glasses, making progress on a long-standing question, which to the best of our knowledge was open prior to our work. And that is to give a rigorous proof of spin-glass order in finite connectivity models. Okay, so the only rigorous proof of replica symmetry breaking, this kind of complex landscape picture due to Parisi, was in these all-to-all models like in figure A there, which is the Sherrington-Kirkpatrick type model. There's been a lot of controversy into what the nature of spin glasses looks like in finite dimensions and whether this RSP picture holds or they're competing pictures, say due to Fisher and Hughes. And then there's this intermediate regime where we're talking about finite connectivity models. It's sparse, it's not dense like A, but we're on this non-Euclidean expander graph. Okay? And there were many heuristic calculations on these types of models using things like the cavity method, but as far as we know, our work is the first rigorous proof of spin-glass order at finite temperatures in this model. And the key point is that in our work, we don't need to rely on disorder at all, and these graphs need not be locally tree-like, which is something these cavity methods rely on. Okay, so this may end up giving us some insight also into structural glasses, which have finite connectivity and no disorder. We prove spin-glass order using this Gibbs state decomposition that I told you about, and this is an explicit measure of a complex free energy landscape. Okay, when you think about spin glasses in this replica symmetry breaking picture, these replicas are heuristically associated with these types of components, but the correspondence is often indirect and subtle, so you'll do a lot of these calculations on RSB, and you want to say that this has something to do with memory and the Gibbs state structure, but we can directly work with that Gibbs state decomposition and prove properties about it. And finally, our method is very transparent. It relies on properties from codes, in particular linear confinement. And while it implies replica symmetry breaking, or at least one replica symmetry breaking, for those of you who know what that is, our methods are completely orthogonal, and in my opinion, much more transparent. Okay, so I'm out of time, so I'll just tell you that the main ingredient that we used for classical codes is a feature called linear confinement, which is a statement on the energy barriers that exist in these expander codes. Okay, in an expander code, you have a linear energy barrier, an extensive energy barrier around code words up to some finite fraction of flip spins. This is actually, again, quite intuitive to understand if you think about how errors propagate and spread on these types of graphs. And this is in stark contrast with finite dimensions, where energy is limited by boundary terms. Okay, so we need the expander graph to get this. And using this and some additional features, you can make very concrete statements about what your energy landscape look like, and not just about these global ground states, but also local minima at finite energy densities. And then with a couple of other more mild assumptions, you can prove shattering and incongruence, and you can also show that various families of these LDPC codes instantiate all the assumptions that we have. Okay? I won't discuss this slide, but this slide is here just to show you how simple our method is. This is it. It's triangular inequality and linear algebra. If I had 5 minutes to walk you through the slide, you would know our derivation. Okay? So, okay, and that's a little bit facetious. We do have 20 pages of supplementary material, but those 2 minutes are enough to get the essence of what we're up to. If you want to get to quantum codes, we need to generalize all of this, okay? And the beautiful thing is that something I've really appreciated over the last 2 years is if you understand classical codes and product constructions, you understand almost everything about quantum codes, okay? Because a lot of the properties of the quantum codes are derived from the underlying classical codes. So we can start with this confinement and bottlenecks in classical expander codes, exploit the product constructions to talk about confinement in quantum expander codes. This generally gives you weaker barriers, but we can prove our bottleneck results even for these weaker barriers. But that indeed required proving a separate technical result, which was this quantum bottleneck theorem. And then combining that with our large code rate, we can talk about the quantum complexity of the Gibbs state decomposition. So to summarize, these spectacular new experimental developments have opened up vast new frontiers in many-body physics, particularly in out-of-equilibrium and non-Euclidean settings. There's much to be done in discovering and simulating novel physics in these new settings. And in turn, this promises new insights into new mechanisms for encoding quantum and classical memories. And the topological quantum spin glass is an illustration of this program.
Thanks for the really nice talk.
Yeah, thanks. Can you comment on the complexity of preparing any of these local minima states, or more generally about complexity of encoding and decoding?
Yeah, so complexity of encoding and decoding. So these are linear codes. So you have some parity check matrix. Getting a basis for the ground states or the code states of that matrix, that's very simple. It's a polynomial problem. And then, if you prepare a ground state, all 0, for instance, is always a ground state or a code word. Once you prepare that ground state, if you just do local detail balance obeying dynamics, that's also simple. So the encoding, in fact, here are some Monte Carlo dynamics that you can just do on systems of thousands of sites. So the encoding problem is easy. The decoding problem is easy, because the decoding problem is just 0 temperature Monte Carlo. So that's very simple. The thing that's hard is gates. And that's a big problem that many people, especially here at IBM, are working on how to do gates in these LDPC codes. Because they protect information so much, because they're so trapped, it becomes very hard to actually do some transformations. So we've been thinking about these codes much more from a topological perspective, and we hope that can help with gates. But that's a much more challenging thing. Yeah.
Hi, thanks so much for your great talk. I'm curious, whereas in the case of the Ising model, you experience symmetry breaking, spontaneous symmetry breaking. In the case of the spin glass, you said that these local minima are no longer related to one another by a global symmetry operation. And I'm wondering if that's actually a limitation or a strength, or is that just completely independent when it comes to these spin glasses as codes?
Yeah, it's just a qualitatively new mechanism. And actually in this problem, because we're talking about codes with a large code rate, you can think of every logical operator as defining a type of symmetry of the problem. So we actually do have all of the ground states related by symmetry. Those are all the blue wells, okay? And now you would say if you have thermally stable ground states related by symmetry, don't we just get usual spontaneous symmetry breaking, okay? But that doesn't show up in the partition function. It's not there. And the reason it's not there is because that ground state actually just carries a tiny, tiny fraction of the total weight. So, and you also have all of these other wells. Okay, so on one hand, you can think of it as like, how do I understand this conundrum? On the other hand, you can see it as like, here's a feature because it's got rich physics, and actually I can embed many different quantum memories in the same physical system. So the effective code rate might even be higher than you had in mind. Yeah. Yeah.
Thanks for the nice talk. So is there an order parameter for this topological quantum spin glass?
Yeah, good. So you can do annealing dynamics and heating dynamics, and you can see signatures of it from that point of view. But even for the classical context, if you move away from those types of dynamics, things like there's something called point-to-set correlation functions, which can diagnose this kind of physics, which actually took a long time to develop. Which diagnoses how correlations behave in these different Gibbs states and what the boundary to bulk kind of effects are. So that we can formulate some versions of that on these locally tree-like geometries, borrowing things from classical codes. But for the quantum version of that, that's still something we're thinking about, because even just defining Gibbs states with quantum memory, there's almost no work on that. So that's something we're thinking about.
Maybe a related question. When I hear words physics of this topological codes, memories, I thinking about the Tory code, and immediately I have think about edge modes, bulk edge correspondence, and all this interesting physics that usually people don't discuss in quantum information. Do you know about anything here?
Yeah, so that's exactly the types of things we're trying to formulate, which is like what, how do we define these nominally live in infinite dimensions? But like if you take a homological perspective, you can start talking about anyons, you can start talking about anyon braiding, condensation, boundaries. So we're building that up. But it's open question. It's hard, but yeah, okay, we're making some progress, yeah. Okay. There's a question back there.
Okay, let's take one last one there, yeah.
Yes, thank you so much. So this is a bit of more clarification question. So here when you're defining the incongruence, so how you're guaranteeing that you will have actually exponentially many more actually local minimas? Because in the traditional definition of the spin glass, we would have actually a lot of metastate. And maybe
a lot of what states?
A lot of non-stable state, metastate, right? And the second one in the picture of the quantum, so the picture usually we have in the classical spin glass and in landscape, we will have barriers in terms of the energy. How we kind of guarantee that also in the quantum sense? Because we will also have some tunneling. Is that like something coming actually from the topological part? Maybe just like more like clarification.
Yeah. So indeed. So that I didn't have time to discuss that at all. So basically you use this feature of having these large energy barriers around ground states, which coding expansion gives you. So this has been proved in the theory of classical codes. And then you basically go from that to arguing that actually that also implies many local minima about finite energy, low but finite energy density states. So that was the slide which I didn't talk about. And that's a combination of a counting argument and some barrier structure argument. So then for the classical codes, we have to do that work to show it, and then we also have to talk about how many there are, make some additional assumptions about how strong the slope is, and then we can show that for that incongruence. The reason we need incongruence is that we already have exponentially many ground states. So to talk about spin glasses, you need every symmetry sector to also be shattered. And then to go from quantum codes, we exploit these product constructions, but that's much, much more. Like I can give an hour-long talk just on the quantum codes, because the barriers are weaker, proving the bottlenecks is harder. But it's basically barriers and bottlenecks are the main ingredients, yeah, which is there for classical and quantum. And the quantum codes do have energy barriers, but then within each well, the Gibbs state looks topological, but you still can talk about energy barriers because it's just a Hamiltonian with energy, yeah.
Yeah, thank you.
Yep.
Okay, let's thank Vedika and all speakers again.